Hello everybody, this is the online replacement session for what would have been our second surveying practical. Make sure you have a look as well at the resources on the KLE in the folder for this session, and if you've got any queries, any questions, then just email me, and as always I'll try to help. So in the first session we've already learnt that surveying is all about measuring distances, directions and elevations. Whatever you want to make a map of, or whatever surveying you're doing, essentially those are the only three things that you're measuring: how far away things are, what direction they're in, and whether they're higher or lower than you are. And we learnt last time about one particular kind of surveying, and that was the traverse survey. And we did a traverse and we talked about having offsets from that traverse. We also last time calculated the horizontal equivalent distances, the HED, and the rise or fall, how much you're going uphill or downhill, by measuring the slope distances and the gradients, and then calculating from those slope distances and gradients what the HED and the rise and fall were. Then it was the HED and the rise and fall that we would put onto a map. And now when we were doing that, in doing the calculations, we saw that there are lots of potential problems arising from separating out the different stages of mapping. If you separate out the data collection from the data reduction, the calculation, and from the map making, then errors can creep in along the way. And if you work through that first exercise last week, you'll have seen that there's a lot of calculation to be done following on from just a relatively small amount of data collection. And the whole process of collecting the data, doing the calculations, making the map can become quite tiresome. Now this week we're going to be looking at a different kind of surveying exercise. The principle is the same. We're measuring distances, we're measuring directions, we can measure elevations. But this time we're going to be looking at the plane table, and we're going to be looking at the technique or the principle of triangulation. Sometimes triangulation is also known as intersection. So if you're looking this up on the internet, looking for training videos and so on, triangulation and intersection are more or less the same thing when you talk about plane tabling. So at the plane table, and you can see there's one in the little picture here on the screen that you've got in front of you. This is from a long time ago, students doing the exercise that you're learning about just now. The plane table is essentially a drawing board on a tripod. And triangulation is a technique that you can use with plane tabling or with lots of other different bits of surveying kit. But triangulation works out the positions of things using directions or angles. Now, the advantage of using the plane table compared with the traverse exercise that we did last week is that using the plane table, you can complete your map in the field in one go. So by the time you come in from having done the data collection, your map has appeared as if by magic in front of you, and you don't have all those tedious calculations to do. You can check that the map makes sense before you return to base, and if you spot any errors, you can go back and you can remeasure those sections while you're still out there. The errors don't wait 3 weeks before turning up when you're back in the lab doing the calculations. And plane tabling is good for doing basic planimetric work with or without heightings. If you want, if you know you're working on a flat or nearly flat site, you can just ignore the heightings component, or as you'll see when we work through this later on, you can make plans, maps of small areas with heights included as well. So there are some advantages to the plane tabling over some other methods. Now, to get your head around triangulation, it's a really straightforward, very common sense if you just think it through in a day-to-day example. So even just if you're stuck in your room at the minute, you can work out how triangulation operates just using your own room as an example. So pretending that this diagram on the top here is your room, or go out and do it in your garden if you like. Just pick 2 points, the red dots at either end of your room or the red dots at either end of your room, 2 points where you could stand from which you can see the other things in the room that you want to map. So we'll pretend that you're mapping the position of your TV in your room, and we'll say that's the blue dot in your room up here somewhere, and we're going to try and make a map of that setup. So all you do is go and stand at one end of the room, one red dot, measure the distance along the room to the other red dot, and that's your baseline, your starting, something you already know to begin with, 2 known points in the room. And from that baseline, you're going to work out the position of this unknown point, the third point, the blue dot. So go and stand at one end of your room and simply measure the angle, the direction from the view looking along the baseline to the view looking out towards your TV. Then go and stand at the other end of your baseline, go and stand at the red dot here and measure the angle between the view looking along your baseline in that direction and the view out to the TV over in that corner of the room. And you can see I've drawn on the map exactly that. So we marked on, first of all, we measured the distance between your two red dots in your room, 4 meters, whatever it might be, and drew a 4 meter long line to scale on your map. So we'll say 4 centimeters on your map, a scale of 1 to 100. So we drew 4 centimeter line in your map and said that's my baseline. Then from here, you measured or estimated that angle between the line of sight along the line and the line of sight out towards the blue dot. And you draw that angle in here with a line of direction out and pointing in that direction towards the dot. Then from the other end, you do the same thing. You measure the angle between that line of sight out along your baseline and that line of sight out towards the TV. Measure that angle there and draw that in as the angle there, giving you a direction out in this direction. You then draw on your map, you extend those lines, which you've measured in at 20 degrees and 30 degrees or whatever it might be. You extend those lines out to the position where they cross, and the position where they cross on your map, that marks the position of where that blue dot belongs on your map. So all you've measured is the baseline, measure the length of that so you can plot a baseline onto your map. Then you've just measured the direction or the angle between the view along your baseline and the view out to your point of interest. The view along your baseline from this end and the view to your point of interest. And that's triangulation. You've made a triangle, you've measured these angles, you've measured these directions, starting from a baseline, and you've fixed the position of your unknown item onto your map. So that's basically how triangulation works, and you can do that more accurately and more precisely by using the plane table, which is what we're going to do, what we're going to talk about in this exercise. So to begin with, just imagine this is your mapping area. So this is basically this aerial view of your field, a bunch of trees in it, or a field with a bunch of sheep in it, or a city with a particular set of buildings that you're interested in mapping the positions of, whatever it might be. You have an area with some features that you want to make a map of. Step one, just as you did in your room, to begin the mapping process, you create a baseline. Lots and lots of different types of surveying rely on using a baseline as a starting point. So this is a very useful thing to get into the habit of doing. A tip is to make sure that from both position A and position B, you can actually see all of these points that you're going to try to be mapping. If you have a great big building or a tree or a 10-foot brick wall in here somewhere, then you're not going to be able to see these points from point B, so you choose a different point B. So try to organize your baseline so that it fits somewhere conveniently across your area, so you have a good view from A and from B of the different things that you're trying to map. Then, as you did in your room, begin by measuring the length of that baseline. Say in our example out on campus or out in your garden, we might have a 20-meter or a 30-meter long baseline. Now remember from last time when we were doing the traverses, if you're measuring something out in the real world and then putting it on a map, you need to be careful that you're not measuring a slope distance. If you're measuring up a gradient rather than on the flat, well then that gradient distance needs to be converted to a horizontal equivalent before you put it onto your map. So if you have a 30-meter long baseline, but it's at a gradient of 10 degrees, well then you're going to need to do that little calculation again that you did last time to convert your slope distance into an HED. That HED you then draw onto the map at the correct length. So if your baseline is 30 meters long and you're using a scale we've said here of 1 to 100, then on your map your baseline would be 30 centimeters long. If you're working on flat ground, then you don't need to convert the slope distance to an HED because it's horizontal to begin with, but if you're working on a gradient, convert it to the HED. At this point, people often ask, well, how do you know whereabouts on your map to put point A or point B? Well, that's easy because you know what area you're mapping. You can look around your garden or look around your field and see how far you're going in each direction. Then looking at your plane table board, you simply say, am I standing in the middle of my area? Am I standing in one corner of my area? Am I standing at one edge of my area? And then wherever you're standing at point A, put that in the right location. So clearly for this example, the surveyor thought, right, I'm standing fairly close to one corner of my area and my baseline is stretching off diagonally across my area. So they put themselves at point A and then drew in point B across their board. Now, they needed to make sure as they were doing this, and this is important, that you orientate the board so that the direction you've drawn that line on your board is actually pointing on the ground towards point B. I'll come back to that later on when we're talking about actually doing the using the board. So I'll run through this step by step in a second, but just to give you a slide that you can come back to and look at if you get confused and want to see where we are in the process. These are the steps that we'll be going through. So we establish the baseline, measure its length, calculate the HED if necessary, and draw that baseline to scale on the map. Then, just as we did in the example where you were measuring the TV in your room, you're going to look from point A along the baseline and out to the point or points of interest that you want to map. Then you're going to go to point B and do the same thing again. Look along the baseline from point B and from point B out towards point X, Y, and Z that you're wanting to map. Then for each of those points that you've looked at from A and from B, where your lines of sight cross over, that crossover marks the position of that feature on your map. So those are the steps that we're going to go through. Now, one bit of kit that goes along with your plane table is something called an alidade. So here you've got a picture of somebody using a plane table, the drawing board, on its tripod, and here they're looking through the alidade. And the alidade is basically a straight edge, like a ruler, with a sight at either end. So you can imagine this is you stood at point A on your baseline, and you're looking down your alidade with one edge of it up against the point A that you've drawn on your map, and you're looking through the alidade and rotating it around until it points directly at point B off in the distance, where you've got your friend holding a ranging pole and you're sighting up to see where point B, what direction point B is in. When you've got the alidade lined up with the point, you then draw with your pencil along the edge of the alidade, and that shows you the direction, both in the real world and on your drawing board, that point B is from where you are at point B, from where you are at point A. So you sight up onto things in the real world for the direction, you then draw that direction onto the board, and suddenly you find you've got your map with everything in the right direction appearing to scale on your board. So this diagram illustrates what we're talking about in that mapping area. You've got your baseline A to B, you've measured that, you've drawn it onto your map, and then from A you take a line of sight by lining up the alidade, not this time with point B, but you swing the alidade around until it's looking at this object here, whatever it might be. You then draw along the edge of the alidade on your map, and it gives you the direction from A to this mystery point, relative to the direction from A along your baseline. You then pick up your plane table and you move, in the real world, you carry it down to point B, you put the plane table on the ground again, get it level, set the tripod up, and then you orientate your plane table so that this line, the baseline, is once again parallel to or in the right direction for the real world version of that line. So this would be you again at point B now, looking back along your baseline to point A, just turning the table around until the orientation of that table exactly matches the orientation that it was in from point A, so that all your directions line up and will repeat themselves. So from A and B, you take a sight onto this feature where the lines cross. You've triangulated from the baseline that you started with, you've now triangulated the position of that feature there. You do that for all the different points that you're interested in mapping, and your map will start to look like this. If you have lots and lots and lots of points, if you have 100 points, which if we were doing this exercise on campus, you may well get 100 points in the afternoon. If you've sighted up onto 100 points from point A, then you go to B and you try to sight up on the same 100 points, you get very confused. So normally we suggest you do half a dozen sightings from A to 6 different points of interest. Then you move your plane table to B, set it up again, and take sightings onto those points from B, close those off by doing the crossovers, and then start on a new bunch of points. So don't do 100 points all at once, do half a dozen or so at once, and label them up clearly on your map as you're doing it. When you've done that, you can rub out most of the construction lines and just leave the little crossover points showing you where your features are, and then you can add your scale, your orientation, your key, and so on, and your map will then appear as if by magic in front of you. If you want to have heights as well, so if you want to spot heights for all these features, well, you can do that using the Abney level, which we talked about last time when we were doing the traverse. The Abney level is that clinometer where you hold it up to your eye, you look through it, and it tells you if you're looking horizontal or uphill or downhill. That gives you essentially a gradient for the ground that you're looking along. If you measure the gradient from baseline point A out to this point, or baseline point A out to that point, you know the gradient plus 10 degrees or whatever it might be. You know the distance because you can measure it off this map. You don't need to measure it on the ground, and that would be a stupid thing to do anyway because it would give you a slope distance and you need to be doing all sorts of calculations. You can measure the horizontal distance, the HED, measure it straight off this map, measure the gradient with your Abney level, and then calculate by this little equation there. You can calculate the rise or fall, the vertical difference, the height displacement between that point and that point. If you calculate that this point is 0.8 meters higher than that point, and that was 100 meters above sea level, well then this is 100.8 meters above sea level. And now you have spot heights for all your features, and if you wanted to, you could then draw in contour lines, which we'll talk about later on in a later session. But essentially using the plane table, getting directions with the Alidade, getting elevations with the Abney level if you want them, you've now got everything you wanted for a survey. You've got distances, you've got directions, and you've got elevations. So the plane table is a really simple bit of kit for doing those essential aspects of any kind of relatively small scale ground survey. It would be hard work using a plane table to map hundreds of square miles, but doing it in your back garden or at an archaeological site or on a river meander that you're studying for part of your geography dissertation or something like that, for small scale local area studies, the plane table is a really useful bit of kit. Once you've got that basic information that we've illustrated on this sketch, well then if you get enough dots and enough heights, you can join up the dots and create a finished map. Now, one thing that students often discover when they do this in the real world, as you might have found also if you work through the previous exercise, is that you think you're doing everything fine, you're doing everything right, you're following the instructions, but then your map comes out looking a bit funny and things aren't in the right places, or something has obviously gone wrong. If you've followed the instructions even approximately correctly, really things shouldn't go wrong. Surveying isn't that complicated. But what normally goes wrong, or the thing that is the most common source of error or problems for students doing surveying, is that you're not doing it carefully enough. If you're a tiny bit out in one of your measurements, then everything starts to fall apart because errors magnify themselves, because you're working at scale and because you're working with angles with diverging lines. If you make a little bit of a mistake somewhere, that mistake can grow and grow and grow and put your map right out. So one of the principles of surveying that you need to be learning at this stage, as well as triangulation and traverse, is precision and accuracy and care. Doing things carefully is a fundamental skill in this kind of surveying. If you do it slapdash, then you'll get dodgy results. So do it carefully.